Afternoon. What we're going to do today is implement the methodology. We're see the beginnings of the formulation of how to implement the meshless methodology into a different type of problem. Okay, so we move from regular diffusion problems, uh, the Poisson equation and steady state, or the diffusion equation, basically the Poisson equation plus the time, and transient mode. Then we move from that to an advection diffusion equation where we can see that a variable, such as the temperature, field variable, can be transported either by diffusion or by advection or convection. Okay, so when the medium is actually moving, like a fluid flow, the fluid flow can carry that energy. Temperature is a form of energy, can carry that energy from one side to another. So not only diffusion is one mechanism, or conduction is one mechanism of transport. Now, this happens too, or the premise up until last class was we knew what the velocity field was. Okay, if we know what the velocity field is throughout the entire domain and boundary, then we can implement it into our equation. It's a single equation for the temperature. It's just that we have an extra term, and it's a term that we have to be really careful about because we have to do the upwinding. We have to do one-sided derivatives. We have to make sure that we satisfy some stability conditions and so on and so forth. But despite that, it's pretty straightforward. Okay, whatever method you're using, all you have to do is add that extra term, and now you know that the temperature or energy can be not only diffused because of conduction, it could also be advected because of convection, because of the medium is moving. Now, what if you don't know what the velocity is? What if you have to solve for it? What if you have certain conditions at certain locations, such as inlets, outlets, and other places where you know that the velocity is constrained, but you don't know the velocity inside this room, for example. You know that there are some vents, and you pretty much know what the velocity is on those vents, so those can be inlets to this room. You know that there are walls, and on those walls, there are certain constraints for the velocity. The velocity cannot penetrate the walls. Okay, the walls are impermeable. Also, the velocity, because of viscosity, cannot slip over the wall. That's called a no-slip condition. And there are certain outlets. For example, under the door, there's a little slit there where the flow can actually get out, and certain other places. So can we set up a domain, throw points around this room and on the boundaries and in the interior, and figure out what the velocity is, and then use that velocity to transport the energy, which is what eventually or ultimately we want to do. We want to determine the temperature distribution. So that leads to another set of equations, which happen to be a little bit more complicated than the advection diffusion equation. They have advection components, they have diffusion components, but they also have other things that play a role. So let's look at, this is advanced modeling methods. Lecture number 23, right? And we're going to look at LRCMM, so the beginnings of the implementation of the localized radial basis collocation meshless method, or incompressible fluid flows. So we're basically looking at CFD. We're trying to build the under the hood methodology for a CFD code. But we're going to use our own technique, the LRC, instead of finite volumes, which is what most techniques use, or most codes, or most packages use. So we're talking about incompressible flows, okay? That doesn't mean that we're only dealing with incompressible fluids. Remember that one thing is an incompressible fluid and another thing is an incompressible flow. An incompressible fluid is water, for example, okay? And an incompressible fluid will always flow incompressibly. Okay, you cannot flow water in compressible mode. However, you can take a compressible fluid, such as air, for example, and make it flow incompressibly. Okay, depending on some conditions. So you can take a flow of air and assume the flow behaves as an incompressible fluid because it satisfies some conditions, normally having to do with the Mach number. Okay, normally when a fluid flows under Mach number 0.3, under 30% of the speed of sound, the fluid behaves as an incompressible fluid. It behaves as such. So we're talking about incompressible fluid flows, which, as I'm saying, can mean, well, flow of air, for instance. Now, incompressible laminar fluid flows, we're going to be talking about laminar flows, okay? In most of my applications, things flow laminarly. Okay, that's not the case when flows are very fast or scales are very large. That's determined by the Reynolds number. Okay, and if the Reynolds number is high, the flow is turbulent, and you have inertia dominates viscous forces, and then the flow actually destabilizes, and the flow is disordered, unorganized. But in my applications, such as, for example, biofluids, okay, in the cardiovascular system or in lung flow, in the cardiovascular system you have flow of blood, and the vessels are, well, the biggest vessel in the human body is the aorta. It's about 1 inch in diameter in an adult, and the whole regime evolved in a way, or it was designed in whatever philosophy you subscribe to, in a way where the flow would always be incompressible, because the Reynolds number in the human body and the cardiovascular circuit is always below about 1,000. 1,000 will be the top. So there's no turbulence in the cardiovascular system. Same as the flow of air within your tracheobronchial tract. The flow of air within your lungs and all that, it will always be laminar, not only because of the flow is, or the velocity is slow, also because the scales are very, very small. The diameters of the tracts and of the bronchi and alveoli and so on and so forth. So we're going to be dealing with incompressible flows. If you're looking for aerospace applications, even automotive applications, then turbulent flows is the regime that you have to be looking at. However, turbulent flow is just an extension of what we are going to be formulating here, and I'm going to be addressing that as the time comes. All right. So these flows are governed by a set of equations derived from mass, momentum, and energy conservation. So you formulate the conservation principles. Conservation of mass cannot be created or destroyed, can only be transferred. Momentum conservation, this is just Newton's second law. That means a force equal to mass times acceleration. And energy conservation, that's the first law of thermal. You take those three conservation principles and expand it in terms of fluid mechanic parameters, those are velocities, pressures, and so on, and then you end up with a set of equations, right? The first equation is the equation that is derived from the conservation of mass, is d dt. And notice that big D here meaning substantial or substantive derivative, plus rho del dot B is equal to 0. So that's mass or continuity equation. Mass or continuity is called the continuity equation. It's derived from conservation of mass. The second equation looks like rho dV dt is equal to minus grad P plus mu Laplace of V plus F. This is momentum. Momentum equation. Okay, that's Newton's second law. You can identify here the acceleration, right? Mass times acceleration is equal to force. Well, this is mass per unit volume, right? But it's in strong form mass. It's mass per differential volume. So what can make a fluid accelerate? Well, it's either the changes in pressure, is the diffusion of the velocity due to the viscosity, or some internal body force, or field force, or some source that is applied externally. Okay? So this is Newton's second law expressed in terms of fluid dynamic parameters. Yes?
Just to clarify, you have, that's delta P, and then rho for dV dt, and then up top, you have the Z.
This is rho,
This rho.
this is rho, this is rho, that's the density.
Okay, yeah.
Okay, this is P.
Clarifying your notation.
This is P. So I'm gonna put a little thing here to denote that it's different. That's a pressure. Okay? And then the last equation we already seen is rho Cp dt dt is equal to K grad T, or Laplace of T, plus Ug triple prime. This is energy equation. And that's the first law of thermal, essentially, right? Conservation of energy, now expressed in terms of the parameters of the flow, the temperature. So this is the equation we try to solve last class or last lecture. We formulated. The velocity will show up here when we split up this derivative into local and Lagrange. But that assumed that we knew the velocity. The whole premise of formulating this equation and the solution of this equation assumed that we knew what the velocity was. Now we don't know what the velocity is. We need to determine that by these other two equations. Now, these set of equations is known as the Navier-Stokes equations. All combined are the Navier-Stokes equation. Sometimes the first two are referred to as the Navier-Stokes equation. This is an addition, but it's coupled with the other two, as you will see. All right. So what do we have now? We have things that we don't recognize. We already know what, well, this, the rho, the density, we already defined. Fluid density. And this is in kilograms per meter cube. And remember, this is a constant. We're assuming it is a constant. We're talking about incompressible flows. Another thing that we see here that we don't recognize, that's new, is P, which is pressure. And that's a field variable. That's why I'm using the dependency. And that's in newtons per meter squared. A property here that we don't recognize is mu. That's the absolute or dynamic viscosity. And that is in newtons seconds over meter squared, or same thing as kilograms meters second. Same thing. And this F, body force, or momentum source, and the units of these are in newtons per meter cube. Some of the things that you can recognize from here. Now let's expand the substantial derivatives, and that's a capital D. So the first one will look like the rho dt plus V dotted into grad rho plus rho del dot B is equal to 0. The second equation will look like rho dV dt plus rho B dotted into grad B is equal to minus grad B plus mu Laplace of V plus F. And the third equation is rho Cp dt dt plus rho Cp V grad T, put a parenthesis here, K Laplace of T plus UG triple prime. There's my three equations. Okay. So now, recognize that the rho dt is equal to 0, and the gradient of rho is also equal to 0, and that's because rho is equal to a constant. We're assuming incompressible flow. So these two terms will go away, this one and this one. And this rho right here, because it's a constant, we can send it over to the other side and it will cancel with a 0. So, expand the set above in 2D Cartesian coordinates such that the velocity is equal to u in the x direction plus v in the y direction. Okay, so now we are going to limit this to 2D, although the generalization of these to 3D is straightforward. All we're doing is just eliminating one of the dimensions. Okay? And again, recognize that the velocity field is a field. This is a vector field that has an x component and a y component. They are completely independent of each other. So, this set of equations will turn out to be the divergency of v of x and t is equal to 0. That's the first equation, because the density goes away. The second equation is going to be rho du dt plus rho v dotted into the gradient of u is equal to minus dp dx plus mu, the Laplace of u of x and t plus fx, the x component of that body force. And now we need the y component of this equation, which is rho dv dt plus rho v dotted into the gradient of v minus dp dy plus mu plus fy. By the way, that fx can also be a function of x and t, and this one can be a function of x and t. And the last equation is the temperature equation, so rho Cp dt dt, which can be a function of space and time, plus rho Cp v grad t is equal to positive k Laplace of t plus ug triple prime, which can be a function of space and time. There's a new set of equations. So we have 4 equations. These are 4 coupled partial differential equations. Why do I call them? Well, I call them partial because there's partial derivatives, okay? The functions that we're trying to solve for depend on space and time. And we call them coupled because we cannot solve one without solving the other. We cannot solve the equation for temperature because we need the velocity, right? We cannot solve the equation for u, the x component of the velocity, because we will need also the y component of the velocity that's embedded in here. We need, this one has u and v in it. We also need the pressure. We cannot solve for v because we need u, which is embedded here, and we also need the pressure. And we cannot solve this one by itself because that's not really a full-fledged equation. This equation can be expressed as du dx plus dv dy is equal to 0. Same thing. The divergency of the velocity is equal to 0. All right, so we have that problem. 4 equations in 2D. It would be 5 equations in 3D. But we need to solve all of them simultaneously. They need to be coupled. And what are the unknowns? If we have 4 differential equations, you have to have 4 unknowns, right? For the system, for the system to be complete. 4 unknowns. These are, well, u, v, p, and t. Those are your 4 field variables. You need to determine those. You cannot solve one equation without solving the other. That's what makes it complicated. One of the reasons why this is complicated. You have 4 tied up equations. They're coupled together. They're partial, second order. Now, what's also complicated about these equations, which is the key complication here? Well, besides the fact that you have coupled partial differential equations, you have 2 more things that would make it extremely complicated to solve these problems. The other thing is that 2 of these equations are nonlinear. Okay, this equation is linear. The unknown is t. The t doesn't show up multiplying t anywhere, right? But look at here. This one has u times the gradient of u. Well, this v has u and v in it, right? It's multiplying u. That's a nonlinear term. That's not allowed in solutions of differential equations. When you study PDEs or even ODEs, you only learn how to solve linear equations. This one here has u and v, and is multiplying the gradient of v. This one is also a nonlinear term. So having nonlinearities in the differential equations is an added complication because nonlinear equations are not even guaranteed to have a solution. And sometimes if they do have a solution, if the solution exists, that solution might not be unique. So you might have non-unique solutions of the same system of equations, bifurcations of the solution or chaotic solutions to these equations. Okay? Also, the third added complication here is that we have the unknowns u, v, p, and t. And I can see an equation for u, I can see an equation for v, and I can see an equation for t pretty clearly, right? This is an equation for u, it's a transport equation. We expand this one in time and advance. This is an equation for v, okay? We set it up as a transport equation, discretize time, advance, and worry about the right-hand side. This is an equation for t. There's no equation for p. That's a third added complication of this system. So you have 4 coupled equations, partial differential equations, 1 complication. Second complication, 2 of them are nonlinear. And third complication, there's no equation for pressure. We have to make it up. We have to create an equation for pressure. You cannot solve for pressure if there's no equation for pressure, right? So, notice that 2 of these equations are nonlinear. So x momentum, notice the term V dotted into grad U. That's the Lagrange derivative of U. That one looks like U du dx plus V du dy. That's how we expand that term in 2D. And this is nonlinear. We have U multiplying the derivative of U. And the y momentum equation, B dotted into grad V, means that U dv dx plus V dv dy. This is a nonlinear. Nonlinear equations are not guaranteed to have solutions, and if they do, these solutions may not be unique. This makes the solution approach more challenging and sensitive. You have to worry about many other things. Okay, so equations are nonlinear. Big problem. Also, notice that there is no explicit equation for the pressure P of x and t. Therefore, an equation for P must be indirectly constructed to be able to advance the solution in time. All right. So now we know why this little equations here can be so complicated to solve, and there's actually no analytical solutions to these equations, only very simplistic forms of these equations. 1D, very slow flow, like Poisson flow, or Couette flow, like cylindrical flow, rotating cylinder, very slow speed, Stokes flow, when the flow is creeping. Very, very specific solutions to this equation, or versions of this equation with high simplifications, would lead to analytical solutions. In the general form, not even in a square. Okay, we're used to saying that there's analytical solutions for equations when you frame them in a square or a circle, when the geometry is nice and framed within a rectangular coordinate system. Not this one's. Even if you set up a square and set up nice conditions on the boundaries, you cannot get a solution to the system. So we need to rely on numerical techniques. Now, we need to set up a time-stepping approach. First, focus on the continuity and momentum equations. And And remember that as seen on or in the previous lecture, the energy equation may be advanced independently once the velocity is determined. Okay, which makes it a little bit more comfortable. There's a one-way coupling between the momentum equation and the energy equation. They're not strongly coupled. It's not a monolithic coupling. That means that we can solve for velocity. We don't need to solve the energy to be able to solve velocity. But we need to solve velocity to be able to solve energy. Is that clear? Right? So if we go back and look at those equations again, see? If we knew the velocity, then we can solve for the temperature, which we saw last lecture. But we don't need to know the temperature to be able to solve for velocity. Okay, so let's concentrate on this continuity and momentum equations. And what we have is the following. All right, so the divergency of V is equal to 0, and rho, I'm going to go back to the compact form. This is equal to minus the gradient of the pressure plus mu plus F. Right? So I'm going to go, I went back to the vector form of the equation. So this is the equation that we broke into two, the previous step. All right, so we have the unknowns being the velocity and the pressure. Now discretize the time. Time as Tn such that n goes from 1 all the way to big N. So we discretize the time as usual and position the continuity equation at time Tn plus 1, the velocity at time Tn, and the pressure at time Tn plus 1 in the momentum equation. Okay, so remember the purpose of a transport scheme that you can advance in time is that you can isolate the things that you don't know on the left and push everything that you know to the right hand side, evaluate it and advance in time. Okay, that's an explicit scheme, right? If we are able to keep V to the power of n, not to the power, but V at n plus 1 on the left hand side and everything on the right hand side, a function of n or the time step n, then we explicitly resolve these. So, but we're going to do a little mix here because it will be impossible to do it explicitly because we don't have an equation for the pressure. We're going to make it up. So we're going to keep this one at n plus 1 purposely. And we're going to position this one at n. Notice that I'm eliminating t, so I'm discretizing the time. plus rho Vx at n, gradient of V at n, and I am purposely positioning the pressure at n plus 1 plus mu at n plus F at n. The body force, which is a known quantity. All right. So we're going to do next what we usually do, which is take that time derivative here and approximate it using a backward differencing scheme. So now approximate the time derivative using a backward differencing scheme. All right, so this now will become and here we have rho V at n plus 1 minus V at n divided by delta t plus rho V at n dotted into the gradient of V at n is equal to minus not the gradient of the pressure at n plus 1 plus mu Laplace of the velocity at n plus f of x at n. All right, so now we're going to rearrange things. And before we do, we're going to let P equals to P at the previous time step plus some phi at n. You can call it whatever you want. We're just making up a new variable. And that's just simply what we call the pressure correction. Such that phi of n is the pressure correction. So the new pressure is equal to the old pressure plus some correction function. And that's what's going to allow us to break off these equations, uncouple them, and make up an equation for the pressure. Indirectly, that is. So what's going to happen is that, let's write this down again. So we have rho V at n plus 1 minus V at n divided by delta t plus rho V at n divided into the gradient of V is equal to, so now here the gradient of P is the gradient of P at n minus the gradient of phi at n. So we broke that up into two. And then we have plus mu, the Laplace of V, plus F. All right. And now we're going to rearrange things. We're going to keep this V at n plus 1 on the left, and we're going to bring this phi here to the left. Divergency of V. And then we have, I have V at n plus 1. And I have plus delta t divided by rho times the gradient of phi is equal to V at n plus delta t mu divided by rho times the Laplace of v plus 1 divided by rho minus 1 divided by rho minus v dotted into graph of v. Is that clear? What we're doing is rearranging things, right? We're keeping this velocity on the left because that's what we want to solve for. We want to advance in time. And we're pushing everything at time step n to the right-hand side. We're going to make this explicit. And notice that this stuff we know from an initial condition, right? From the previous time step, we know the velocity, we know the pressure. At time step n, we know everything currently. So we can advance in time. So if we take the previous velocity and the previous pressure, which we know, get the Laplace, get the gradient, get the Lagrange derivative, which we know how to calculate using meshless methods, add this up, and then we have this, whatever this is. It's not directly v, but it's v plus this. Now what we're going to do is take that left-hand side on the second equation and let v star equals still v at n plus 1 plus delta t over rho This is so-called intermediate velocity. It's an intermediate velocity that is a result of transporting and advancing the velocity in time. Okay, so what we're taking is, this is an artifice. This is a mathematical trick. I'm taking the left-hand side and calling it something else. That doesn't have a meaning for us. Doesn't mean anything. It's just some intermediate quantity. Also, recognize nu as mu over rho. See this quantity here that shows up? Mu over rho. That's called the kinematic viscosity. And it's in units of meters squared per second. Remember that I told you that all diffusivity coefficients have units of meters squared per second? The kinematic viscosity is the momentum diffusivity coefficient. So this is called the momentum diffusivity. Sometimes called the relative viscosity or kinematic viscosity. It's just the viscosity divided by density. Turns out to have the units of diffusivity. And that's basically what that is doing there. This is the diffusion term. This is the diffusion of momentum. So, if we apply this, we get divergency of v at n plus 1, which we don't know what it is yet. We don't know what v at n plus 1 is. It's v star, which is equal to v at n plus delta t nu Laplace of the velocity plus 1 over rho, forcing term, minus 1 over rho, gradient of the pressure, minus the velocity dotted into the gradient of the velocity. That's the Lagrange derivative of the velocity. All right, now notice that the momentum equation is an explicit equation. It's explicit. That means everything on the right-hand side is known from the previous time step, and is an explicit equation for the intermediate meaningless B star. We don't even know what that B star means. It's just we are advancing in time and we get B star. So now what do? We got a transport equation that is explicit. We got a useless velocity, B star, and somehow we got to make sense of these and be able to use that to find V at n+1 and to find the pressure at the next time step. Okay, so far we haven't done anything. What we have done is just rearrange the equations to make it look pretty, but useless. Now, here's a trick. How can we use this to determine the new solution? V at n+1 and P at n+1. So what we're going to do is introduce the correction equation into the continuity equation. Which one? We're going to take this equation right here, right, and plug it into this equation to see what happens. So that is a continuity. And the correction equation is correction. All right, so we solve for V at n+1 from here. Is equal to V star, which we already know, plus delta T over rho, sorry, minus delta T over rho, radian of phi. Plug that in here into continuity. It's equal to 0. And see the divergency of the gradient is the Laplace, right? Del dot del is the Laplace. And delta T and rho can come out of that equation. So that would lead to the Laplace phi is equal to rho over delta t, the divergency of V star, which is already known. So the right hand side is completely known. So this is a known right hand side. How do we call that equation? The Laplace of something equals to a known quantity. How do we call the equation the Laplace of something equal to 0? The Laplace equation, right? So when we have a forcing term, we call it the Poisson equation. We solved it many times in this class, right? We solve it using dual reciprocity methods and boundary elements. Then we solved it using meshless methods. So we know how to solve this equation. We know the right hand side, we just determined it at every point. So now all we have to do is solve this equation. This is a Poisson equation for the pressure correction Pn of x. We can employ any of the already described techniques, such as the dual reciprocity BEM, or we can use the RBF meshless method to solve it. Okay? So we already solved that equation a ton of times. It just looks a little differently because this is not the temperature, it's just something else. And the right hand side is not U, but it's something else, so we know. So, note that this equation must be solved at every time step. Again, making it the bottleneck in the solution process. Right? Because every time you want to advance in time, you need to solve for a new phi. And to solve for a new phi, you need to solve a Poisson equation. You know how long that takes. We know how long that takes. You have to do it with boundary elements or with meshless methods. You have to form a collocation matrix or an influence coefficient matrix, apply boundary conditions. And why do we need to solve it again and again and again? Because the right hand side changes. This is continuously changing. The V star changes at every time step because we're advancing it in time. So the Poisson equation kind of remains the same, but the right hand side, the forcing term, changes. So this is the bottleneck of every CFD solver. That's why CFD solutions are very slow. Because at every time step, you have to solve a full problem, a full Poisson equation. All right. Now, once is determined, well, once the Poisson equation is solved, we can use it to update V and P, such that, well, this is how we first define what phi is. It's the pressure correction. So once we determine phi, we can update the pressure this way. Now we have a new pressure. And once we no phi, we can update the velocity like this. So problem solved. It's easy to say, but a lot of things went on at every time step to get to the new time step. So the new field at time step n plus 1 is determined where the new velocity v n plus 1 is guaranteed to satisfy continuity. That is, the divergency of v is equal to 0 because that's what we set up. That's how we arrived at the Poisson equation, by enforcing that. That means that at every time step, no matter what you do, if you solve the Poisson equation correctly, the velocity is going to be solenoidal. It's going to be divergency free. That means satisfying continuity, satisfying conservation of mass. And it's obviously very important to satisfy conservation of mass. Okay? If you don't satisfy that correctly, if you don't solve that Poisson equation correctly, and you don't update the velocity correctly, then you'll be creating mass or destroying mass. So mass will tend to disappear or appear within your scope, within your system. All right? So now we can advance to a new time step by following the same exact procedure. That is, determine V star such that V star is equal to V ln plus delta T times whatever that bracket. Determine Vn such that the Laplace of Vn is equal to rho over delta T times the divergency of V star, which we just found. Update P is equal to Px plus phi, and update V such that V n plus 1 is equal to V star minus delta T over rho gradient of phi. And this is the solution process. Advance in time, advance in time, advance in time until you reach your final computation time. Final solution time, which you predetermine in the input file. All right. Now what else do we need? Any ideas? Everything is based on the premise that you have initial conditions, so at n equals 0, you know the solution, you know the velocity, you know the pressure. Right? But what else do we need to solve? This is a boundary value, initial value problem, right? So what do you need? Boundary conditions, right? You need boundary conditions for velocities, you need boundary conditions for for whatever you have equations. We have an equation for these and we have an equation for these. We don't need boundary conditions for these because, see, they're updated automatically. So, let's write down boundary conditions. We need to set up boundary conditions for the field variables. We're going to establish, there's a few more boundary condition types, but we're going to establish 3 types of BCs. So we're going to establish row 0, walls, so that's type 0, row 1, inlets, and gamma 2, so gamma 0, gamma 1, and gamma 2 outlets. So walls, inlets, and outlets. With that, we should construct a fluid mechanics problem, a CFD problem. All right. So let's start with type 0. Walls at gamma 0. So those portions of the boundaries that we assume to be walls, let's say this is the walls of this room, the roof, the floors, and the perimetry. So at walls, what do we say about the velocity? What is the velocity on the walls? 0. Not only the normal velocity is equal to 0, meaning that the velocity cannot penetrate the wall, the velocity can also no slip. So both components of the velocity, u and v, regardless of the angle of the wall, must be 0. This is called a no slip condition. Because of viscosity, the velocity is kept at 0. So you can see this is the first kind Dirichlet first kind condition. Now we're solving a Poisson problem, a Poisson equation for phi. So what do we do with it? We need a boundary condition. And we're going to arbitrarily specify a homogeneous condition for phi at n as the phi n dn, and by the way this is at gamma 0, at gamma 0 is equal to 0. And as you can see, this is a Neumann second kind condition. So phi is kept at 0 normal. Okay, there are implications to that. We're arbitrarily saying this, but it's not so arbitrary. There is an explanation of why this one would have 0 normal derivative. It implies the normal derivative of the pressure doesn't change. It implies other things, but mainly, I'll tell you at the end, okay, once we set up inlets and outlets. So we have walls. Right. All right. So we don't need an equation for P or a boundary condition for P. We don't need a boundary condition for P, as this is updated from, again, I'm going to write it down one more time. So, everywhere. That means domain and boundary. All right. inlets.
Bring it down just.
Bless you. At the inlets, what do we know about the velocity? At gamma 1, so we know the velocity is prescribed. At an inlet, you either know the mass flow rate or know the velocity, which one is the other, right? So again, this is a Dirichlet, first kind condition. And again, let the phi dn at gamma 1 be equal to 0. Again, this has implications and explanations, but at the end I'll show you the most convincing argument for these. Human second kind condition. The pressure is updated automatically, the same way. Type 2, outlets at gamma 2. So now outlets, it's a little bit more intricate because outlets really don't exist. An outlet is an open boundary that we decide to cut at a point and say from this point on we don't care about what happens to the fluid. But the fluid still exists past the boundary, right? It has to go somewhere. We're just saying at this point we don't need to know anything about it. So we need to be careful about how do we set that up. Normally, what we know at the boundary is the pressure. At the outlet boundary, at gamma 2, there is a prescribed pressure boundary condition. So this is a prescribed pressure. And what do we do with a prescribed pressure? It basically means, this means that, remember from the correction equation, and we set this up at gamma 2, gamma 2, gamma 2. So this one is equal to that prescribed boundary condition, and this one is also equal to that prescribed boundary condition. Right? It doesn't change in time. If you set up the pressure to be something, you can also make it change, but you know what it is. So therefore, phi n at gamma 2 is equal to 0. So this is Dirichlet, first kind. Now, a common condition for the velocity field at the outlets is that the normal at gamma 2 is equal to 0. This is very arbitrary. This pretty much says that the velocity right next to the outlet boundary is equal to the velocity at the boundary. Okay, the normal derivative is equal to 0. Although commonly used, these condition creates stability problems as it is known to reflect information back to the domain. That means, well, instead of flushing it out, because that's what you want. You want the information to be flushed out. So if this is an inlet and that's the outlet, and the flow is going in that direction, you want all that information that includes velocity and pressure to be flushed out. But if you set up this as a boundary condition for the velocity, what's going to happen is some of the information, the wiggles, the pressure waves, are going to hit the boundary, and some of them are going to try to reflect back into the domain, and those will interact with the incoming waves, and it'll create perturbations and instabilities. Okay, so this is called a reflected boundary condition. It's a way of faking a condition for a fake boundary that doesn't exist. Remember, the outlet boundary doesn't really exist. It's just an open boundary that you say, well, things are going to flush out through there, but the fluid actually continues to flow somewhere. So what you want to do is make sure that everything goes out through the boundary. When you set something up like this, some of the things are bound to reflect. Okay, we're going to address this one on Thursday, but before we leave in the next 30 seconds, I'm going to tell you that notice that all boundary conditions for the pressure correction phi of x are homogeneous. So the pressure correction equation, remember, is rho over delta T or delta T over rho. The rho over delta T. Rho over delta T times having homogeneous PCs ensures that if the right hand side vanishes, the solution will be equal to 0. And that's what you want, no correction. Essentially, converged steady solution, steady state solution. So that's what will happen if you solve this equation with all homogeneous boundary conditions, first kind and second kind, and eventually, as time progresses, this correction of velocity, because intermediate velocity goes to 0, which is as expected. It should go to 0 as everything winds down to steady state or an asymptotic solution. If you have an equation that is equal to 0, equation is homogeneous, and all boundary conditions are homogeneous, the solution is trivial. There's no pressure correction, you arrive at the final solution. So that's the argument to make, or to fake, not to fake, but to actually construct homogeneous boundary conditions for the phi problem. All right, so there's much more to this than what we've shown today, but in an hour and 15 minutes, I've shown you how to solve fluid mechanics problems, or CFD problems. In next class, we're going to address this specifically with the localized collocation, RBF collocation method, and we're going to actually set up a better boundary condition for the outlet boundary, and we're going to implement it in the code and see what kind of solutions we'll get. And now I already have an idea of what to assign for the final project, which will have to do with you implementing something on this code and creating a geometry and finding things out from that geometry as to what the behavior of the flow would be. All right, so that's it. I'll see you on Thursday.